Please ask everyone to join the class. Please ask your friends to join the class. Okay, I'm sharing my screen, okay? Screen is visible? Is my screen is visible? Okay. So let me know if the video is
The
audible
basis
or
of the
not and
virtual work
both are
method
lagging
and
or
its use for
it is
calculating
okay.
joint displacement in trusses were discussed in Lecture Essay 21. In this lecture, I'm going to show you how this method can be used to calculate deflection and slope in beams. Let's start by reviewing the method using a truss structure. Consider this truss. Under the applied load, it is
In
going to
this class, we'll
displace
see the
like
method of
this.
virtual work for beams. Okay. Let me know if it is
To
okay or
determine
not.
joint displacement, say horizontal displacement at C, we place a virtual load at the joint. In this case, a horizontal load at C. Note that the direction of the load corresponds to the direction of the target displacement. If we are seeking to find a horizontal displacement,
Is
the
it okay?
virtual load should be horizontal. If we wish to calculate a vertical displacement, the virtual load must be
Okay. So I'll
vertical.
start with this beginning. Okay. So I'll start with the beginning. Very few students came. Anyways, let's start the class.
The
So see
basis
method
of
of
the virtual
virtual
work method
work.
and its use for
So method of
calculating joint
virtual work with
displacement in
for
trusses were
beams. Okay.
discussed in Lecture Essay 21. In this lecture, I'm going to show you how this method can be used to calculate deflection and slope in beams. Let's start by reviewing the method using a truss structure. Consider this truss. Under the applied load, it is going to displace like this.
So it is reviewing the
To
last
determine a
class
joint displacement,
method of virtual
say
work for
horizontal
presses.
displacement at C, we place a virtual load at the
So
joint.
those who have
In
missed the
this
first
case,
class,
a
they
horizontal
can
load at C.
understand.
Note that the direction of the load corresponds to the direction of the target displacement. If we are seeking to find a horizontal displacement, the virtual load should be horizontal. If we wish to calculate a vertical displacement, the virtual load must be vertical. In this case, external virtual work equals P star times delta, and the internal virtual work equals here, F star I is the force in member I due to the virtual load, and delta I is elongation of the member due to the real load. According to the method of virtual work, external virtual work equals to internal virtual work. P star is the applied virtual load, and F star I is virtual member force due to P star. This is displacement due to the real load, and this is member elongation due to the real load. Now let's turn our attention to beams. Say we have this simple beam. Here is how the beam is going to deflect under the load. Suppose we want to determine the vertical displacement at mid-span. To do so, we should place a virtual load at the midpoint of the beam, where deflection is denoted by delta.
Toko, mute yourself.
You are the main businessman in businessman. Every sale of product को लगता है. इधर आ रहे तो फिनिश में बड़े ये फास्ट में क्या ऑनलाइन रेड दिस.
Then the expression for external virtual work can be written as P star times delta. To determine the expression for internal virtual work, we need to know two things: the internal member force due to the virtual load, P star, and the internal member deformation due to the real load, P. What is the main internal force in beams? Bending moment. When dealing with beams, we generally consider bending moment to be the only internal force that contributes to the structure's deflection. But since bending moment is not constant throughout the beam, we need to express it using an equation. Here, the virtual load is placed at the midpoint of the beam. Therefore, the beam's virtual internal bending moment can be written as. Now we need to determine the internal deformation in the beam. To do so, let's examine a tiny segment of the deformed beam. Since the beam has been deformed under the real load, the segment also has a deformed shape. We can treat it as an arc length of a circle. The angle facing the arc length, this angle, represents the internal deformation of the segment due to bending. So, internal virtual work in the segment can be written as m star times d theta. To determine internal virtual work for the entire beam, we need to integrate the expression over the entire length of the beam, like this. But before we can use this equation to calculate internal virtual work, we need to express d theta in terms of dx, since m star is a function of x. Let's start by referring to the length of this segment as dx. This is the infinitesimal length of the tiny beam segment. Also, let's refer to the radius of the circle containing the arc length as rho. And keep in mind that this deformation is caused by the bending moment produced by the real load. I'm going to show the bending moment as big M. Using simple geometry, we can write d theta times rho equals dx, or d theta equals 1 over rho dx. Now we need to express rho using more familiar terms. There is an interesting relationship between rho and m. When m increases, rho decreases. When m decreases, rho increases. Interestingly, the product of rho and m is constant. More specifically, rho times m equals E times I, where E is the material's modulus of elasticity and I is the moment of inertia about the axis of bending. Of course, here we are assuming linear elastic material. Then we can write d theta equals m over EI dx. Finally, we can write the expression for internal virtual work for the entire beam as. It is important to keep in mind that m star is bending moment equation due to the virtual load, and m is bending moment equation due to the real load. The virtual work principle can now be written as. If we assume a unit virtual load, we can determine delta using equation. Delta equals the integral of m star m over EI with respect to x, where both m star and m are in terms of x. Let's calculate delta at the beam's midspan. We determined m star for this beam earlier. Here it is. Note that m star and m equations are defined over different intervals. To make the integration work, we need to divide it into 3 parts, as shown below. If we assume a constant EI for the entire beam, we get so vertical displacement at the beam's midspan is. Let's go ahead and calculate vertical displacement under load P as well. Here is the moment equation due to P. It is the same equation we used previously. Now replace P with a virtual unit load. Write the moment equation due to this unit load. This is going to be the same as M equation, where.
So if you see in this beam, they have been asked to find out the virtual displacement under the given load. So in the first phase, this part, in the first phase, they have found out the deflection for the given load under this P. P by 4, 3P by 4, these are the reactions. Okay. These are the reactions. Okay, so they have found out the moment for this beam for this condition. For first from 0 to 6, that means if you consider from 0 to 6, the whole length was 6 plus 2, 8 meter, right? So for 0 to 6, what is the bending moment equation? Px by 4. And from 6 to 8, that means from this part to this, the bending moment equation is this. This is for the real conditions. Now they have considered a virtual condition also. Okay, so for the virtual condition, they have replaced this P with 1 and they have found out the moment equations. Okay, these are the moment equation under the virtual load. These are the moment equation under the P.
P is replaced with 1. Therefore, the virtual work equation becomes. Here, since the moment equation intervals match, we can write.
So they have used this equations m dash m by ei. So they have this 1 by ei is common, so they have taken out and they've
This gives
replaced the
us
m dash
delta
with
equals.
these equations: x by 4, 6 minus 3x by 4,
Here's another
and they
example.
found out the
A
deflection
cantilever
that.
beam subjected
Now
to a
let's see the
uniformly
example of
distributed load.
cantilever beam
Let's
with
calculate its
UDL.
vertical deflection at A. Assume constant EI. We start by writing the moment equation for the beam. Now, remove the real load and place a unit virtual load at A. Write the moment equation due to this unit load. The virtual work method equation is. So vertical displacement on the cantilever at A is. Suppose we are also asked to determine the slope of the elastic curve at A. This can be done easily using the method of virtual work. Here, since we are looking for slope, denoted by theta, we are going to place a virtual unit moment at A. This way, the product of the rotation and virtual moment is virtual work. So the expression for external virtual work becomes 1 times theta. The expression for internal virtual work remains to be. However, now m star is the moment equation due to a unit virtual concentrated moment applied at A. So the cantilever's rotation at A is. We will examine the use of the method of virtual work for calculating deflection in frames in the next lecture.
So these are the two problems. You can take the screenshots and you can find the solution also. Okay. Now let's see one problem. Screen is visible. Screen is visible. Let's solve the last problem we saw. Calculate the horizontal displacement and the slope at C. Okay. So they have converted into this. Actually, this is a fixed. Actually, this is a cantilever beam, fixed at support, and this is the overhanging part, and a load is applied. They have shifted it to in the vertical frame. Okay. So the screen is visible. Is my screen is visible so that I can play? Okay. Carefully see the solution of the problem. Okay. This cross section is 10 by 10 and this cross section is 10 into 20. And E is 2 GPa, 200 GPa. First they have found out the I value, moment of inertia of. There will be two moment of inertia for AB, this part AB, as there is there is a difference in cross section. So I value for this part and this part will be different. So they have found out the I value. As it is rectangle section, so I will be BD cube by 12. Hope everyone understood the problem. Let's see the next problem. Okay. So they divided the beam into two parts. This is the first part, this is the second part. On the first part, UDL is acting, and the second part, there is no any load. Okay. They first of all, they have I will be same throughout the beam. Okay, the cross section is same, so I will be same throughout the beam. So I will be as it is in rectangular shape, so it will be I BD cube by 12. Okay. So they have found out the moment equations from for 0 to 4 and then 4 to 8. So this point is considered as a hinge point. Okay. So this is also a method to find out the deflection and slope with the help of virtual method in this problem. Okay, I'm repeating this video so that you can go through the solution once more. Hope everyone understood. Okay, I'll share the video also so you go through these videos, the last class work energy principle and the today virtual work method. Okay, so write your roll numbers in the chat box. Anyone left to write their roll number? Twenty-three, 24, 40, 13, 1, 30, 45, 12, 46, 9, 19, 26, 14, 29, 3, 2, 33, 20, 11, 22, 18, 4, 25, 28. Anyone left to write their roll number? Those who wrote their roll number, they can leave. Is anyone left to write their roll number? Okay. Write your roll number. Okay, note it down.